In the previous lectures, we have shown that we have introduced the concept of multiplicative process or multiplicative dynamics, which essentially imagines that there are a lot of, let's say, individuals whose wealth, Wi, evolves in time according to a rule which says that it's the wealth at time t plus 1, it's the wealth at time t times some kind of random number. And we have shown that even if the distribution of those random numbers evolves in time and it's not stationary, as long as it is the same for all the participants, and as long as there is some kind of social security, let's say, by not allowing any of them to go beyond a certain, below a certain fraction of the average wealth of all the others, one obtains Pareto power law, which essentially says that the probability for wealth, the probability distribution of their wealth depend on the wealth itself by some kind of decaying power alpha, which in fact is determined, it's independent on the variations in the multiplicative number. So in a sense, it's independent of whether the entire economy is growing or decaying or doing anything else. But it depends only on the ratio between the social security lower bound and the average wealth in that society. So this is a quite non-trivial result, because it relates the wealth distribution of the richest and of the middle class, which is characterized by this exponent alpha, as we have seen, in fact, in some real graphs. It connects it to the social security, which is applied to the poorest. So it is a kind of global effect which emerges out of a dynamics which is applied at the individual level. And this is going to be a recurring theme in this course, in obtaining some kind of global collective dynamics in the economy or in other social systems in terms of so to speak, a microscopic view, an individual view, in which the laws are pretty simple, even though their expression at the macroscopic level is sometimes looks complicated. So what we are going to do now is to connect further, to continue this way of making connections between simple things which happen at the individual level and involved things which happen at the global level, by asking whether this model which we just defined and which is after all so simple, whether it can explain what we see in nature about the stock market. And what do we see about the stock market? First of all, the stock market is an important thing, not just because some people get rich or not on that, but it's actually an expression of what is the capital of that economy, of what is the wealth of that economy. And the fluctuations in the stock market are in a sense, we already got used to that, but they have a striking characteristics. There are millions of participants, and if you think about random system, even people which were not exposed to such a course, they know that the fluctuations in a random systems are proportional to the square root, and therefore when normalized to the entire population, it's 1 over square root. And therefore, they over the square root of participants, and therefore for millions of participants, you expect that the fluctuations are of the order maximum tenths of % or things like that. And we see that the fluctuations in the stock market are occasionally much larger than that. They at least 1 order of magnitude, but in fact even more than what you would expect. So we are going, in fact, to show that this is a very expected behavior in view of the model which we just defined. So we are going to define something which is called the square standard deviation. This looks like a very scary term, square standard deviation, but it says something very simple. You see, I want to know what is the size of the jumps in this process. What are the size in the jumps of the average wealth, or which is of course proportional to the sum of the wealth of all the participants. So it's in a sense the entire wealth in the system, which therefore somewhat I related to the stock to the index of a stock market. And I'm saying, look, what I'm interested in is what is the amplitude of the fluctuations, not whether they are plus or minus, because if I look at whether they are plus or minus on a short range, the plus and the minus cancel very much. But what I'm interested to measure is also the amplitude of the fluctuations, which of course is very important for the kind of risk which I'm having. So in order to do that, instead of taking the average, let's say, of these variations in time of W, I'm taking the square of it. And I'm making the average of these squares. So even if something goes up, down, the sum of the squares, or the average of the squares, can definitely will still can have a very large value if each of the jumps, both up and down, they are large enough. And we are going to find that indeed, for that particular system that we were discussing, in which the WIs have a Pareto law, have a power law, and in which the variation of each of them is proportional to themselves by the very dynamic, the multiplicative dynamics which we defined, then their sum is going to have this quantity, which typically would be a finite quantity. It will be infinite. Huh?
What does that even mean?
What does it mean, infinite? Well, it's in the second line. In theory, if I take an average over an infinite number of such numbers, of these squares.
Why would it be an infinite number in the stock market? Why would the stock market be an infinite number?
Well, you see, the point is it's not so much whether there is an infinite thing. The point is that if I have millions of people which are involved in it, as opposed to, let's say, 10 people, then what is interesting for me is to take to consider what will be the limit, what is the behavior of the system when this number of steps goes to infinity. So you don't have to think about infinity in the philosophical level of the actual infinity, but you have to think of the fact that these systems, and this is part of the message of what I'm saying, these systems have even though they are very random, they have a very ordered behavior when you take this limit of very many participants, okay? In the same way in which if you send a coin, if you send it once, then you don't know what is the result. If you send 10 times, you don't know what is the result. If you send it 1 million times, you know what is the result.
So you can only
50% would be face, and 50% would be, I don't know how it's called in English, the other side of the coin. Does anybody know?
So you can only see trends like with a lot of
Yes. So we are speaking about trends. While for a normal process, you will see that this measure of how large are the fluctuations will be something finite. For this kind of system which we just defined, the fluctuations will be in fact very, very violent, and they will be exactly as we see them in the stock market. In fact, we'll give a very much precise quantitative relation between the behavior of the fluctuations in the stock market and between the Pareto law, Pareto distribution of the people wealth in that society, and between the what we have done already between this Pareto exponent and the social security policy within that society. So we are going to have a quite impressive conceptual unification of three different things, which a priori would think that they are unrelated. And again, this is the kind of ethos I'm bringing from this sciences campus. We like to explain very many different things by just, if possible, by the minimal possible amount of assumptions. This kind of conceptual unification, it's for some people a fascinating game, which we mean understanding, which we call understanding. You can, I'm aware that in other domains you can call understanding something else, maybe related but complementary. But this is a kind of game which I'm going to play now. And again, you will see there is, so to speak, a lot of mathematics, but every single line which I introduced, I was thinking of you audience. By now I know it, all of you. And I tuned, again, it's not a matter of intellectual capacity at all. It's a matter of just speaking in a language which either you know already or which I'm introducing, because otherwise I cannot expect to have this communication. So the point is that we'll find that the fluctuations of the wealth, which is represented by the stock market index, are not going to be microscopic, some fluctuations which don't interest anybody, but they are going to be quite large, and they are going to be related with the alpha, which we already computed in terms of C. So we'll have this unification between the social security as applied to the poor in terms of the C number, between the inequality in the society as expressed by the Pareto exponent, and between the financial instability in the markets as expressed by this amplitude of the fluctuations and their behavior, which instead of being, in the case, let's say, when alpha is equal to 1, in place of going like T, as small fluctuations go, they will go like T squared. You'll see this. I'm not expecting yet you to understand, because this is what I'm teaching today. And again, I just have chosen the example in economics, but this kind of fluctuations, sigma squared and things like that. The reason that I decided to spend a lot of time on them is because I know that these are very much of use not only in the social sciences, but also even in the humanistic sciences. And therefore, it's even if the final results, I find them very exciting, but even if somebody might find them outside of one interest, the very material which we are going to learn is going definitely to be useful for anybody which deals with social systems. So let's consider a series. According to our names, I'm calling it U0. You remember that we have our steps, they were of the type 2 to the n sometimes. So I'm calling this series to U0, and it's going to be plus minus 2 to the 0, which this is a fancy way to say that I have a series of numbers which randomly they are plus or minus 1, and I'm taking for the moment that the probability of plus and minus 1 to appear is equal to half. And then I'm defining the average of such a series. And now we are getting again to what is the limit to infinity. If I take the first one, well, the first one, it's either plus or minus. It's not 0. And if I take the first three also, it's minus 1. It's not 0. But if I take very many of them and I take the average, then of course, if I have as many pluses as many minuses, then the average of this series is going to be 0. So I'm taking very slowly. What I'm saying is partly information and partly just definition. This is what I mean, the average of such a series. Each value which the series can take, which in this case it's either plus or minus 1, multiplied by the probability for such a value to appear. Understood? That's very important. The average of a series is just, a sequence of numbers. And in this particular series, I take that the numbers can take only the value plus 1 or minus 1. And like throwing the coin. And then you are gaining or losing $1 time. And then I'm asking what is going to be the average of what you gained and what you lose. And then I'm saying, well, it's +1 multiplied by the fraction of, by the percentage of the +1s which I expect to have, -1 times the number of -1s. And since the probabilities are 1/2, and then it's 1, it will be plus half, -1 half, 0. Okay? This is the average. Now let's go to the, and this is how I would show it on a graph, okay? This is a +1, -1, +1, -1. Now comes the story with the square standard deviation, which now you understand what I mean. What I want to know is not what is the average, but I want to know what is the typical distance at which one step gets me from the previous. So I take the squares of 1, and so from this point of view, from the point of view of the distance to the average, +1 and -1 are at equal distance. So if I take the square, then I get exactly what I want, a measure of how far away one step gets me from the average. Understood? So essentially, this series here, in terms of the squares of +1 and -1, now in terms of taking +1 times the probability of +1, -1 times the probability of -1, now I'm taking +1 to the squared times the probability of +1, and -1 to the squared times the probability of -1, which of course is a fancy way to say that I'm taking essentially both of them 1, and then no wonder that the average is 1. As in fact you see it here. 1 corresponds to 1. -1 squared also corresponds to 1. So the series of this series squared is in fact a constant, and therefore it's not a wonder that the average of this constant is 1. So in this case, it is obvious that by defining this kind of a quantity, which I call the square standard deviation, the square standard deviation is just the average of the squares of these deviations, which is the series itself. And in this case, it's 1. So it's a little bit boring, but you'll see that towards the lecture it gets more involved. So I'm taking it slowly. So I'm asking for the ones which are bored by this just to have a little patience, and for the other ones to stop me here, because as I go on it gets more complicated. Now, of course, if I take another series, I will call it U1 because I take it ±2 to the 1. It's 2, -2, and so on, of course. And I take the same probabilities for +½ and for -½ Now, of course, this series is differing from the other one by almost nothing. Now I have +2 times the probability of +2, -2 times the probability of -2, and again, obviously, I'm going getting 0. So you see, it's 0, but it's 0 only when I take an infinity of numbers. Otherwise, there is always some kind of deviation between having exactly 50% on pluses and minuses. And now I'm saying again, let's see the square standard deviation. This time, the square standard deviation is the square of this, plus the square of this, plus the square of this, plus all these other squares, divided by their numbers. This is a standard deviation, and of course, all of them are 4. Because -2 squared and 2 squared are both of them squared, and therefore no wonder that the standard deviation comes out to be 4 without much computation. I'm doing this because I want you first to understand the principle of how we act. In a short time, we will have computations. It will not be so simple as having just everybody having the same distance from the average, from 0. Okay? Good. So now, since we worked before with those things which were 2 to the n, I take the series un, and of course I have the same story with, except that in place of 1 or 2, I have 2 to the n minus 2 to the n, each of them with their probabilities. And I think that this time I really bored you to death by that time. I hope that everybody understands that the average is always 0 because there are as many ups and downs, but the square the standard square deviation is always positive, and all of them are equal to the same thing, 2 to the n squared, which is 2 to the 2n, as you remember. Good. So now let's go to something a little bit more complicated. Suppose that I'm taking I'm taking two series now, U0 and U1, and I combine them. So in place of having just plus minus 1, I have now plus 1, minus 2, minus 1, minus plus 1, some kind of random combination of the two things with equal probability. In this particular case, I take that the probability for 1 to appear, for plus or minus 1 to appear is half, and the probability for plus or minus 2 to appear is half. And between them is also half, so each of them is a quarter. So again, then of course I will have a situation in which I have the average of the entire series would be the average of the first one times the probability for terms from the first one to appear, plus the average of the second one times the probability from the second one to appear. But since the averages of both plus and minus 1 were 0, then of course I get 0 also for this series. So not a big surprise here. Now let's see what happens with the standard deviation. With the standard deviation, essentially, again, I have I put it a fancy sigma squared, sigma 0 squared. We know what is sigma 0 squared. It's just 1 because both plus squared, plus 1 squared and minus 1 squared gives me 1. Therefore, I have 1 times the probability to either plus 1 or minus 1 to appear, which I said that it's half, plus 2 to the 1 squared, which is 4. Times probability 1/2. So it's essentially 1 plus 4 multiplied by half, because both of them are half. It gives 5 to the 2. But graphically, so 5 to the 2 is not such a round number like before, but it's clear from where it comes. It comes from the fact that I have some of the numbers here are 4 and some of them are 1. By my choice before, I took that the numbers of 1s and the numbers of 4 are equal, and therefore I have the average between 4 and 1, which is 5/2. Good. Okay, so now it's finished with the trivial examples. Now we are getting to the to something a little bit more involved. What I really want to do is make an average for the kind of probabilities, as you remember, which were of the type that the probability of 2 to the n was 2 to the minus n, or proportional to 2 to the minus n. That was the kind of probability I had for the wealth of people. But we said that the variation of the total wealth in the society is the variation of each of them, and the variation of each of them, because it's a multiplicative process, is proportional to what they are. So therefore, it is clear that what I have to do in order to understand the fluctuations of the total wealth of this thing is to understand what is are the fluctuations of a series in which the different participants are of the size of distributed by this probability, Pareto probability, which we computed before. So this is what we are going to do. It's again, it's not a trivial computation, but I've invested a lot of things. Instead of investing in understanding new stuff, I invested in just putting the old stuff, the things which are known in a form that it's really communicable without a lot of jargon. So let's start slowly again. I have the probability of plus minus 2 to the 0. I call it P0 because of this n. And I take it 2 to the minus 1 because I want the normalization. I want to have 1/2, 1/4, 1/8. And if I go to infinity, then the sum is 1. You remember, we always had a normalization issue. But in any case, they are proportional, each of them with n, except that there is a minus 2 to the minus 2 in front of everybody. So I have P0 is 2 to the minus 1, P1 is 2 to the minus 2, and P2, which is the probability of having plus minus 4, it's 2 to the minus 3. I'm taking, meantime, just 3 terms. We'll take all of them in a short while. And the average, again, it is the average of 0 times the probability for 2 to the 0 to appear, for the plus minus 1 to appear, plus the average of the series with plus minus 2 multiplied by its probability. And but it doesn't matter because all these m's which we have computed, and they are 0, all of them. Therefore, the average of this series is 0. Now let's see what happens about the sum of the squares. The sum of the squares in this particular case, I could write sigma 0 squared here, but you remember it's actually equal with u0 squared, because u0 is either plus or minus 1, and squared is 1. Therefore, it's essentially, this is 1, this is plus minus 2 to the 1, which is plus minus 2. So this square is 2, it's 4. And this one is 4 times 4, 16. And each of them with the probabilities which I associated with their occurrence. So essentially, you see, I'm saying, look, I have the ones which are half of the guys which appear. There are the fours, which are 1/4 of the guys. And there are the eights, which are 1/8 of the guys. So if I show only part of the series, this is more or less how it's going to look, the squares which contribute to the standard square deviation. If I take more, then of course I will have something similar. So let's put the numbers here. As I said, u0 squared is 1 to the squared, u1 squared is 2 to the squared, u2 squared is 4 to the squared, and their probabilities I just put it 1/2, 1/4, and 1/8. And there is this normalization, because as long as I don't take the entire series, it is not true that 1 plus 1/2 and this is 1. So there is some normalization, but this is almost 1. I'm not, you can forget about it. The point is that each term, this one gives 1/2, this one gives 1, this one gives 2, which means that it's essentially 1/2 times 1 times plus 2 plus 4. And if I would continue, you can guess, but you don't have to guess because this is the next slide. The main point is already then you see that it is not so difficult if we think systematically about this to understand what is the standard deviation of this series. Okay? Now, again, you see that for the standard deviation, it's a finite number here. If I have steps of reasonable size, then of course the standard deviation cannot be larger than the yes. You have some question?
I was about to decide if I want to ask the question, so I'll ask it anyway. Right, what we see here, we see that the probabilities of it being higher and higher, the probabilities are lower and lower.
Yes.
But over here in this calculation, you just got to 2 to the second, and not to, I mean, obviously in very low
wonderful, thank you.
You can have a very high...
wonderful, that's exactly,
really
this is exactly the point. You see, there is going to be a lot of mathematics, but you just said in words what this mathematics is going to say. The mathematics is going to say that if the steps are larger and larger, even though their probability is smaller and smaller, if their probability is not going fast enough to 0, as they go faster and faster, you still have a situation in which their size times the probability is still larger, increasing. And that's exactly why it's going to be a situation in which the standard deviation is going to diverge. Because in spite of the fact that you say, okay, but these very large steps are now 1/8, and next time they are going to be even less probable. So these things will never happen. Well, that's one of the things which we are going to discuss. How much they happen and how much they do influence the actual behavior of the standard deviation, of the fluctuations in the process. So you see, there is this single guy here, which is 16, but he appears only once, but it's more than the sum of everybody else. So this is exactly the point, and this is exactly how the stock market behaves. So you can explain in great measure the stock market by saying, look, I know why there are these such fluctuations, because there is some kind of microscopic aggregation of wealth, either because the wealth is concentrated in one single hand, or maybe because the guys which are bidding there, they are themselves concentrated by forming a herd or by influencing one another. So this is in order to remind you that in fact this is the case, that the people which are appearing there, they have orders. This is a double logarithmic scale. Each of them it's by a large factor larger than the previous one. So this is and each of them are acting within the market. So actually I'm a little bit boring because now I'm taking 4. But now I will go fast because you already understood. I have the standard deviation of each of these steps of size 1, 2, 4, 8 with their probabilities. So essentially, in general, I have 2 to the 0 squared plus 2 to the 1 squared, because plus minus 2 to the 1 squared is 2 to the 1 squared. And 2 to the 2 squared, 2 to the 3 squared, and multiplied each of them by their probabilities, 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4. And some normalization factor which is getting closer and closer to 1. I just don't want to even discuss it. It's only when I rehearsed this lecture, I noticed that if I start speaking too much about this, then I'm missing the main point, which I want to make, which you already made. If I take the minus 2 outside, because in any case it was some normalization for the probabilities, essentially I have 2 to the 0, because times 2 to the 1, because it's 1 times 2 minus 2. This is 2 by 2 minus 2. It should be. Okay, this is actually true. So basically, I get 1, 2, 4, 8, and so on. And again, it's not such a wonder. This time I just copied the previous thing, which had 16, and another time 16. But now I have also a 64. Now, this 64 is very important because it's larger than anybody else around. This is a real contribution to the entire story, the 64. And the 64 would not appear if I would have taken a shorter series. That's important. This is we are going to take into account this. I'm using all the time the word mathematically exactly because the mathematics is so low. So I'm trying. So this is the entire point, that for a finite sample, the most important things don't appear. And we'll see that. But in any case, now I'm going to write no, even this is not in general. I'm now taking 6 terms. And again, it's 2 to the 0 squared up to 2 to the 6 squared, each of them by their probability 2 to the minus 1 up to 2 to the minus 7, and this factor which is basically 1. But this, it's 2 to the minus 1 times the sum, as we defined, this sum from k to equals 0 to k equals 6 of 2 of k squared, 2 to the k squared, times 2 to the minus k. And I know how much is, and therefore it's a sum from k from 0 to 6 of 2 to the k. But we remember sum of x to the k is x to the k plus 1 minus 1 divided by x minus k. So I have the 2 from here, but essentially I have 2 to the k plus 1 minus 1 here. And therefore it's 2 to the 7 minus 1 over 2, which is similar to the numbers which we get before. It was always it was, for instance, 15 over 2. So this is probably 255 5 over 2 or something. No, 500, 612 probably. So, the basic point is that now I have an even larger guy appearing. Each time that I try to take more and more terms into account, instead of the thing converging to something, which would happen if they would have more or less the same size, out of a sudden I discover, wait a minute, but there are guys which are even bigger than that because of the power law which I had. So in general, what you get when you look at these fluctuations on a long range, you see this kind of a graph and this kind of distribution. Now, this is Paul Levy, the guy which discussed this kind of behavior almost 100 years ago. And by the way, they were telling about him, he's not a real mathematician. Why? Because he was dealing with this kind of intuitive stuff, not things which just Prof. Now, in order to have more intuition about what these graphs mean, I'm showing to you how these graphs with plus minus 1 or the order of plus minus 1 look. They look like this. You don't have these spikes. And everybody is concentrated on a very narrow thing, and also on a semi-logarithmic scale, their behavior is like this. It's very thick in the middle, and it goes essentially to nothing very, very fast. You don't have more than 5 standard deviations. While here, you see that you go very, very far away. You have very large fluctuations. So this is the intuition of this. And we are going to make this more precise. Because you see, maybe this kind, after you said essentially in 2 words more or less what is the bottom line, you might think that it's a little bit pedantic to do a lot of mathematics just to say the same thing. But it's not like this, because when you said what you said, somebody else, maybe from what you are studying? Economics, okay. If it would be somebody from philosophy, he will say, no, but it's actually well, I could think differently. So the question is not whether I could think differently. The question is to put in a very precise way your statements. In fact, some of my colleagues in economics, when I'm saying to them, look, you are not very successful in predicting things, and they say, no, you don't understand. We are using the mathematics not in order to get predictions, because we know we cannot, but in order to make our thought precise enough so that our colleagues would understand exactly what we mean and what are our statements. Now, in this course, I have both this and, as you see, also things which are, and this is why I take the pain of coming from the other campus and give this lecture, because we also have predictions which are validated in a Popperian way too. But it also makes the things precise. So now we are going to all this boring is going to pay, because now I'm going to make it formally. In place of 2 to the n, I'm taking m to the n. So the probability of having plus or minus m to the n, you remember it was proportional to m to the minus n alpha, where alpha was decided by my lower bound. And I take with n going to infinity. What means n going to infinity? I want to see what happens when I take n larger and larger, okay? You don't have to, and you shouldn't think about, when I say something about infinity, about the actual philosophical infinity, because this is going to get us only in trouble. Nobody can imagine infinity. Okay? But we have a way, you'll see now, in real action, how I take, what I call, I take the limit to infinity. You will see immediately. And now the sigma of each of these components, of course, I know what it is. It's the probability of plus is mn to the squared, plus half the minus mn to the squared, which means that the standard deviation of each of these terms by itself, it's m to the 2n, of course.
Is that always the equation?
This? This is this one?
The one under.
This one?
Yeah.
No, I'm arranging the computation such that I don't have to use integral and things like that, because I'm saying, look, I have now a combination of steps. Each of the sizes of the steps I know with which probability comes. And I know what is the square of these steps. M to the 2n. You see, the probability of m to plus or minus m to the n to appear is m to the minus n alpha. This we computed last time. Is the size of the wealth of the people, and we said now that the variations of the sizes, it's also proportional to their wealth. Therefore, this expression says that that in this particular little bit caricatural situation in which I take multiplication by m, but m doesn't have to be an integer, but I take multiply by m or divided by m, then I get the power law, which means that I get that the only values which I'm considering here are m to the n, and the probability of each of them to appear is m to the minus n alpha. That we obtained. It's a mathematical way to say what you see here. That 2 to the 0 appear very many times. 2 to the 1 squared appears not so bad. But 2 to the 7 or 2 to the 6 appears essentially only once here. So this is what this probability means, that as I take 2 to the n with n larger and larger, the probability goes lower and lower. Okay? And this is how it goes lower. We got it. We got it really, you know. And now I have sigma squared. And we said that the sigma of the combined series, in which I'm taking all the possible values of the steps up to a very large value, which I'm keeping it now undefined, but I want to take it larger and larger and see what happens when I get larger and larger. This is what I mean by taking the limit to infinity. I have the sum, the way according to the convention which we said. Probability of a step of rank n to appear, and the sigma n of that side. But we know that this sigma squared is just m to the 2n. And Pn, it's just from here, m to the minus alpha. So I have a sum from n equals 0 to a very large n of m to the minus n alpha, which is the probability, times the square of the steps, which is m to the n squared, which is m to the 2n. Okay? Up to here, it's clear? Is it clear? Good. Because now what I have to do is I apply this kind of manipulations of exponent which I ask you to know by heart. So m to the minus n alpha 2n is equal to m to the minus n alpha plus 2n. Then I take n outside, and then it's m to the power 2 minus alpha n. And then this is also equal to m to the 2 minus n to the power n. Are all these steps known to you? I intentionally made them, you see, 4 different steps. Usually I would just throw this thing here.
But usually you're working with math students.
Exactly. So no, I'm trying to explain that there is an utmost effort in all this explanation, that there is no jump whatsoever. If you don't have to know anything in advance. Just follow the flow of operations. So now but now, in my jargon, I was telling, I call this x. Okay, the sum of something to the power n, it's equal to 1 minus x to the n plus 1 minus over.
Why are you calling it x?
Because I proved once forever that whatever I have here is going to be equal to 1 minus whatever minus this to the power n plus 1 over 1 minus this. Whenever I have a sum like this, with anything which, it doesn't matter what I have here, this is equal to this. This we have done in the class and also in the exercises and also in the explanation sheet. Do you remember this formula? Yes. So I'm applying this formula to this sum. This sum is exactly of this type. Sum over something, and the power n goes from 0 to some very large value. And this is the value of this sum. It's just 1 minus this thing to the power, you see? M to the 2 minus alpha is M to the 2 minus alpha. Yes? And to the power n plus 1, large n. It's this n plus 1. And here it's 1 minus this thing.
This is for like multiplicative.
This is called how is it called? Geometric sum. Remember the word geometric sum. It's the sum of the powers of k of x from 0 to n, and it's always equal to that. And and let me put it in this way: if you think that you have to learn by heart millions of such formulas, the answer is no. This is the only formula. But actually, I was astonished myself of how much you can do in life with just knowing one single formula. We used it 2 or 3 times until now, and we keep using it from now to the end of the course. So you please remember this thing, and please rehearse it at home. Anyway. So sigma squared is now equal to this formula, which is essentially 1 minus whatever appears here, m to the power 2 minus alpha, over 1 minus this thing. Now, this part is not that important. The most important term is this one. Why is this important? You see, if alpha is larger than 2, then you have a number m, which we always took it larger than 1. It's m to some power, which is a negative power, which means that this quantity is less than 1. And if I take a quantity less than 1 to a very large power, then that thing gets smaller and smaller when I take n to infinity. And therefore, and this is what I mean by taking n to infinity. You see, if I suppose that m, look here. Suppose that m is equal to 10, okay? And suppose that alpha is equal to 3. Then I have 10 to the minus 1 here, 0.1, okay? And suppose that n I'm taking now 1, then it's 10 to the minus 1. If n is it's 2, then it's 1 over 100. If n is 100, it's 10 to the minus 100. It's 0 for every purpose. Therefore, I can neglect this, and in the limit, and the words which I'm saying when I'm saying that is that the limit of this, when n goes to infinity, if alpha is larger than 2, this is 0. This, you see, there are situations in which I take something to infinity, which means I take this larger and larger, and nothing happens after some time. This gets smaller and smaller, and eventually it gets 0. And then the result would be just 1 over 1 minus a constant. So for alpha larger than 2, this sigma squared, is, when I take n larger and larger, I get to values of sigma which are closer and closer to some constant, which happens to be proportional to 1 over 1 minus m to the 2 minus alpha. It doesn't matter. It's a finite number. That's important, which means the fluctuations which you have seen on my graphs, they are limited. If I keep going, they are the distance to which I get by continuing my series of numbers, random numbers, at some stage gets stationary. It doesn't behave. Now, as opposed to what? How can it be differently? It can be differently because if alpha is less than 2, then and m is larger than 1, then this is a number which is larger than 1 to a power which is very large. So this entire thing, this sigma, explodes. It's proportional to this. The one is negligible, this one is negligible, and the only thing which is important is m to the 2 minus alpha, which is a number larger than 1 now. Some number which is larger and larger. It's like 10, 100, 1000. As I go on, if alpha is less than 2, which is in fact the case. Remember, alpha is the Pareto exponent. Alpha is essentially, it tells me about the distribution of wealth in society. And in reality, alpha is equal to around 1.4. Sometimes in some countries it's 1.2, in some countries it's 1.7. But it's definitely between 1 and 2. And therefore, this is the case in nature. This is the case in nature. The standard deviation, as I take n to infinity, when I take into account the entire sum, I get infinity. I don't have, and this is people which are in the stock market, they call it volatility, more or less, this sigma. And this volatility goes to infinity. So we have deduced in a very simple way, and maybe because of this simplicity, the connection to the reality is a little bit blurred, because you say, well, maybe people are doing differently. But we'll see that not only I give this qualitative explanation, but I'm going to show that the fluctuations of the market, indeed, even quantitatively, they do respect this behavior. And this is what we are going to do now. In the meantime, I'm, so as I said, alpha is typically, I was generous putting 1.1. Usually it's larger, and usually it's less than 1.8. But it's definitely less than 2. So we are in this. So we are in the. Sorry. So we are in this definitely in this case in nature. So now I'm going to ask the following thing. Of course, dealing with infinities, it's complicated, and it's complicated for everybody. And in fact, it's a little bit misleading, because when I have a finite number of measurements, no matter how the stock market is fluctuating, it will never be infinity. So the question is, okay, I'm speaking about infinity in the limit that I run it for a trillion years, and but of course the market is not going to rest for a trillion years. So I can ask some other question. What is the maximum, if I have a finite amount of time that I'm looking at the market? What is the largest step which I'm going to see? What is the largest fluctuation that I'm going to see? As you remember that when I showed that graph, there was a 64 there, which appeared only once. And I said, if I would have had a longer run, maybe 64 would have appeared more, maybe also 128 or something else would have appeared. So for each number of steps, for each number of steps in the series which I have, there will be an expected size which is the largest. And I know how to compute it, because I'm saying the following. If I know what is the probabilities for each of the sizes to appear, let's say I know what is the probability for m to the n to appear. It's m to the minus n alpha. Remember that, yes? That is a thing which I would like you to remember, this formula, because we worked a lot to obtain it.
That's 2 formulas.
Yes, that's 2 now. But this one we obtained using this one. So I'm not sure whether it should count twice. Anyway. So the point I'm saying is the following. I know what is the probability for m to the n to appear. It's m to the minus n alpha. And I'm saying, if I have a number of steps which is such that the number of steps times the probability is less than 1, it means that the probability to obtain in that number of steps one step which is of that size is very small. The expected number of steps of that size to appear in let's say, t steps, is going to be less than 1, and therefore it will not appear, if t times that probability is less than 1. Therefore, the size of the maximal size of a step, which I expect in a finite time, as opposed to taking the average over an infinite time, is given by this equation, time, the number of steps, time m to the minus n alpha. And this gives me what is the n, which is the maximal, which I can expect. And therefore, I can now put t on the other side and take the 1 over alpha power here. And therefore, I get that m to the n maximum, the largest step that I expect to appear within a time, within a number of steps t, within a time t, is t to the power 1 over alpha. Understood? You understood? What I'm saying here in a more symbolic way is that if you have a probability 1 over 1,000 of some event to appear, then if you make 100 trials, it will probably not happen. Most likely not happen. Because it happens 1 in 1,000 times, and you made only 100 times. So this is what I'm saying. The largest, there are many events, many sizes, and some of the sizes just do not appear. There is one maximum which can appear for each number of steps. So maybe I should, it's like here. You see, I have a finite number, and this is the largest step which happened. If I would take a longer time, then I would have a larger step. Because I know that for each size, I have a certain probability, which is going according to this formula which I ask you to remember. So having a size of this size, or maybe of this size, it has a lower probability. It just doesn't appear in 10 to the 6 steps, in 1 million steps. But it will appear in 10 million steps. So this is what this formula says. That if I am in this regime in which alpha is less than 2, which is the regime in the real economic system, and it is not in a typical random walk, Gaussian random walk, then the largest step will go like t to the 1 over alpha. Now I can return to the formula of sigma squared. Because you remember, I got this formula, that sigma squared was proportional to m to the 2 minus alpha n. I show you here. That was the last formula which we got, that for alpha less than 2, sigma squared goes like m to the 2 minus alpha n. And we said, oh, but if I take n to infinity, then if I take larger and larger, then this sigma will get larger and larger. And now I say, no, it's not so simple. This is what, if I take average over an arbitrarily large sample of the stock market, but if I take it for a finite time, then the largest step, it's not n, but the largest step is given by 2 to the 1 over alpha. So I'm going to make that sum again, but this time with the maximal step, which I know it is. So instead of having sigma squared m to the 2 minus alpha n going to infinity, I'm saying, no. Sigma squared would be, first of all, I have to multiply it by t, because it's t times, I have now t terms, like t individual terms. But what I'm going to have to take here is not n, but n maximum, because these sigmas are taken out of a sample, of a finite sample of t steps, and therefore there is not an arbitrary n which can appear here, but only up to steps which have at all any probability to appear in such a finite step. Like if it is 1 over 1,000 probability and I have 100 steps, then that step will not appear.
What's the difference between n and p?
Huh?
What is the difference between n and p?
Where is p?
Sorry, n and t.
T is the number of steps which I'm taking in reality. N was a hypothetical, n is essentially saying how many sizes of steps I'm taking into account. So I said, okay, I have steps of 2 to the 0, which is 1. I have steps of size 2. I have steps of size 2 to the 2. I have steps of size 2 to the 4, and so on. Up to 2 to the n. Actually, not up to, but up to nothing, up to arbitrarily large values. So this large n was essentially a way to saying that I'm going to take 2 to larger and larger values, but since I don't want to write the word infinity there, then I take 2 to the n, and then I see how it depends on n.
So it's the increments of the steps?
Yes, it's how many steps I take. This n is, look here what I said. This sigma, it's the sigma of a series which contains everybody of size 1, everybody of size 2, and everybody of size 2 to the n. I'm not taking, if n is 1 million, I'm not taking the steps which are 2 to the 1 million and 1, even though in principle I should. I'm not taking because I want to see what happens if I take it more. I write first the formula, and then I say, oh, if n is equal to 1 million, then I get, and let's say alpha is equal to 1, then and m is 10, then I get m to the power 1 million. If I take 1 million and a half, I get 10 to the 1 million, 1 million and 1, which is much larger. And therefore I say, aha, so my dependence on n of this previous formula is essentially that it explodes to infinity. And now I'm saying, well, I have second thoughts about it, because what I'm really interested in is not what happened if I take an arbitrarily large sample in which even the largest steps, any steps of any size appears. I'm taking just, let's say, 2 days of stock data. And in these 2 days of stock data, there are, let's say, 1 million time steps. And therefore, what I have to take into account is among this 1 million of time steps, I have to take into account only those ones which have any chance to appear at all during 1 million steps, because the other ones have a probability which is less than 1 millionth, and therefore taking 1 million steps does not guarantee that they will appear at all. So this is why I substitute now n max, which we computed before. We computed that n max is t to the 1 over alpha. I'm substituting it now instead of n here. So I'm taking instead of m to the 2 minus alpha n max, I'm taking, first of all, I can write it n max 2 to the minus alpha. And now I'm putting 2 to the alpha here. So the sigma squared of t steps, it's t because there are t steps. But it's sigma, not of the sigma ideal of an infinity of realizations of the system, but the sigma which is obtained in reality when I do have only t steps, and therefore the largest size which appears is 2 to the 1 over alpha. Understood? And now it's simple. I just multiply here, it's 2 over alpha, and this 1 over alpha times alpha is 1, and this one with this t goes, and I get the final result that the square standard variation of the fluctuations of a market after t steps goes like 2 to the t to the 2 over alpha. That's important because it's essentially the measure of how large are the fluctuations which I expect in the market, and now so this is a very strong prediction because it says go to the statistics which says what is the distribution of wealth in your society, let's say Britain or in United States. Compute alpha of Pareto. Write down that alpha. Now go to and look at the fluctuations of the market how they depend of how much time you wait. You wait 1 second, you wait 10 seconds, you wait 100 seconds, you wait 1 month, and this will increase the number of steps. And I'm saying the sigma which you obtain, the typical distance which you get, the typical variation within such a time, will depend on the time, like t to the 2 over alpha, where alpha is the thing which you measured when you measured the wealth of the people in that society. This is a tremendous unification, which normally in economics people would have not thought about it. You have to have this kind of physicalistic model in order to start making this kind of connections. Now, these steps are very large, and because of some they are rare. So what we actually measured in order to prove that what we were speaking about is true was the following. After all, we are speaking here about the probability distribution of the fluctuations. So the integral of the sum of all the probability has to stay 1. So if I want to draw something. So suppose you have some distribution, probability distribution, and the integral below this curve, it's essentially has to be equal to 1, because the sum of all the probabilities for the different values of, let's say, the return of this difference between the index of the market at some stage and the index after some number of steps t. So there are different values for that. So the sum of all these probabilities have to be equal to 1. Therefore, if the width of this function goes like t to the 2 over alpha, actually to 1 over alpha, because it's the square root of sigma squared, then the height has to go like t to the minus 1 over alpha. So, as time goes on, you have, of course, flatter and flatter distributions. You have more and more probability for very large variations to appear. And therefore, the probability to have the same value now as you had 1 month ago is much lower than to have the same value which you had 1 second ago. So, and this goes like t to the minus 1 over alpha. So for small t, it can be relatively high. It will look like this, as in fact I showed to you the graph. But for large times, it will look like this. So you look at the height of the probability distribution of the returns of this variation of the value of w after t steps. And you make the prediction that it's going to be related with an exponent which is 1 over the exponent of the Pareto law. I gave right now, as opposed to the very strictly mathematical things, now I made a little bit, I also used the word integral. So I would like to check whether you understood what I'm trying to say. So I say, okay, so this explains. So I have this distribution. You remember, this is not Gaussian. It's Gaussian would go like t to the 1 over 2. But this one, Levy distribution, goes like t to the 1 over alpha. So it gets wider and wider, but then it gets lower and lower. So essentially, for measuring alpha, you can either measure this width, but then it gets more and more noisy and less reliable, or you can measure this height of this distribution. And again, I remind you, the prediction of the theory of this, and now it's a prediction which you obtain together with me here. It's not some voodoo something very, very, the model is very clear, the manipulations are very clear. You predict, this is a logarithmic scale, so equal factors are represented by equal distances. So you see that when you take the time in equal factors, 5, 50, 1000, then they will go like this. And in fact, this was a measurement which was made by one of my co-workers, Professor Golo. And what she did was the following. She used data from French and Fama. Fama got actually the Nobel Prize either this year or the last year for more or less this kind of it's called the efficient market hypothesis, but it's actually at the heart of the model which I described, and I will discuss it next time probably, maybe even today. But look what she did. French and Fama have on their internet site, they have the index of the market for every month for the last 88 years. So every month they have the index of the some kind of a stock market. It's not only Standard and Poor's. It's some more aggregated index of the market. But it's a good proxy for the wealth, for the capital, which is common to the entire people which are invested in that market. And now. She did the following thing. She took time intervals of 1 month. So she looked at how much there was a variation between the index this month and the next month. And she counted how many times a certain value is obtained. So the value 0, that you get exactly the same thing like this month and the other month, is very high, while the values that, let's say, they are differing by 2% is smaller, okay? There are fewer instances in which the difference between, so on the x-axis is the difference between this month and the next month. And on the y-axis it's how many instances you get that particular difference. Except that in place of having only for this month and the next month, you have also graphs. The graph for this month and next month is the black one, but there are these other colors which are for differences between this month and 2 months ago, this month and 4 months ago, this month and 8 months ago. And you measure the tip of the height, which, as I said, it's related with the width. And indeed, you get a straight line on a double logarithmic scale, which essentially means that indeed it's a power law. And the slope of this straight line is essentially the exponent of the power law. So returning to where we were, essentially, what was measured there was this exponent. And now the question is, does this exponent equal the Pareto exponent, the exponent of the distribution of wealth of people? So I'm going to show this now. So not only it is true that indeed the variation of the stock market as a function of the time over which you take this variation goes like a power law, but when you compare it with the Pareto exponent, which some of you remember, this graph appeared very many times. It's essentially the wealth on a double logarithmic scale, the wealth of the different people as in the order of their of their wealth. This one is Gates, this one is Buffett, this one is Allen. These are the Walton family. And they have equal values. This is Ellison, Dell, Balmer, and so on. So the prediction of our model is that the slope here and the slope here, the slope obtained from the measurement of the wealth of people within that economy, and the slope obtained by seeing how this distribution of returns in the market changes in time, one gets the same value. And indeed, these were measured very carefully by Moshe Levi, which is now a professor in finance here at the Hebrew University. And you see that even though the values of alpha in different countries are not really equal, because they're, remember, this is related with the social security value. Alpha is 1 over 1 minus c, where c is the ratio between the poverty line and the average. So in different countries, there are different policies. So alpha, Pareto is different. But always alpha Pareto is now, according to our model and according to the experimental measurement, it's equal to the exponent which characterizes the dependence of the fluctuations of the market with the span of time over which you are measuring those fluctuations. So not only we explain why the fluctuations of the market are not microscopic and are so large, but we actually give the, a quantitative prediction, which is in fact, which was in fact confirmed by the data. So these are some simulations made by Professor Golo. These are for different time variations. As you see, indeed, they are equally distanced because the time were by a factor larger, each of them. This was for alpha equal 2. And this is a comparison between this alpha, which was obtained, which is this function which is obtained by plotting those points as a function of the time difference. So it's this. And this is compared with the Pareto law, with this alpha. And as you see, they have the same slope as predicted by the data. There are some finite size effects related with the fact that, in fact, the number of people is not infinite. And here, the last 2 points are what you would get if you would have a Gaussian distribution, the normal kind of noise, which is different from what we have here. So we see it's a very different slope. This is another example with alpha 1.45, which is very close to the typical values in nature. This is for alpha equal 2. And there is, this is for alpha equal 3. Do you remember what do we expect for alpha equals 3? Do we expect to have similarity between the alpha of Pareto and alpha of and the exponent of the fluctuations? You remember that we got this special effect only for alpha less than 2. For alpha larger than 2, this effect is not there according to the theory. And indeed, according to the numerical thing, you see the 2 lines are not parallel. This is the Pareto law. If the inequality between people will be such that alpha Pareto is larger than 2, which means that you see almost everybody have the same wealth. It's not anymore that there are very people which have much more than the other. Then the fluctuations of the market would be with alpha would be essentially Gaussian. So this kind of closes this entire. This is another example for alpha less than 1, which is very thick, but you still get for alpha less than 2. This is actually even less than 1, but for anything which is alpha less than 2, then you see the two exponents, the one of the fluctuations of the market and the one of the inequality of wealth of people are very much the same. Okay, as I said, this was confirmed. Okay, good. So now I pass to something which is much more easy. I'm also myself very relieved to show pictures from now on, but I would stop now for asking for questions. We are basically finished with this particular issue. Okay? Okay. So now everything which I showed to you is related very much with a concept which you probably heard very many times. What is this? Sorry. Oh, okay. Which is called fractals. I actually checked last time and checked that actually I shouldn't assume that people know what are fractals. So fractals are essentially the kind of situation in which we were before. That you have, instead of having some series which is more or less uniform, you have from time to time much larger fluctuations, which are in fact quantitatively, in fact, dominating the rest of the behavior. So this is also called intermittent. Situations in which the rarest events are the ones in which are in fact the most important. And this goes a little bit against much of what is assumed in many sciences, including in physics many times, that you take the average, the typical behavior, and then you know what the system does. And there are systems in which, no, it is not the typical behavior, it is the outstanding exceptions which are dominating what is really going on with the system. So here, it's a schematic way of what we had before. There we had the different steps. Imagine that this is the wells of the size of the steps, or and this is some time. And intentionally, I took it regularly in place of having the probability of a certain size to be fixed. I'm taking even the position to be fixed. So I have the smallest values here, which are so dense that they look like a continuum. But they are actually like here, except that the width of the line is so big that you see as if it is continuum. But there are many of size 2 to the 1. These are 2 to the 2, 2 to the 3. Only the 2 to the 4 are rare enough that you see them as independent. However, I can zoom in and say, look, I want to, essentially what I did was dividing everybody by 2 and declaring that whoever is less than 1, I don't want to look at it. So essentially, all the guys which were at 1, I don't look at them, or the guys which were 2 to the 2 are now 2 to the 1. And so on. So this is why now you see the guys which are of the order of 2 to the 2 already, they are rare enough. So you see the system is essentially similar to itself. When I look more and more deep into it, I still, the general shape is preserved. So this is one way of characterizing fractal. It's a series or a picture which when you look at the different scales, it looks self-similar. And I hope that when I say that, you do look back onto what we did until now today to realize that we essentially were dealing with this kind of system. Of course, here I'm taking rarer and rarer, I mean smaller and smaller value, and I'm not taking longer and longer times. If I would take longer and longer times, I will have guys out of a sudden which are of course larger than 2 to the 2, but they are just far away, and we don't see them here. So it's again a realization of the point which I was making, that you do not see the largest guys if you have a finite sample. And sometimes this is very important because they are, in fact, the ones which might be the important ones. This kind of self-similarity was observed in very many other domains. For instance, if you look at the boundaries of a lake, actually the famous example was when people started to measure the boundary of Britain. Not boundary, of course, the coast of Britain. So at the beginning they have some techniques, you know, with telescopes looking 1 kilometer away and taking the distance. So they got some distance. And then somebody, as technology appeared, then they could make it much faster. So they made with a meter, so to speak, which is not 1 kilometer away, but is, let's say, 100 meters away. And they got a completely different value. Why? Because if you go in straight line, you get like this. But if you, in the meantime there is some change, then you get longer. And as you get shorter and shorter in length, you get completely different value of that number. It's not like okay. So this is what is shown on this little lake in Florida. That as you go zoom more and more, all kind of features which you didn't see before, they are apparent. And of course, it also goes backwards, as I discussed. If I would have started here and then got larger and larger, then I would have discovered that this, instead of these little things, I also have this kind of very large islands appearing. So it goes in both directions. So we can systematically analyze this kind of series, except that now, you see, instead of speaking about probability, I'm saying I'm taking values which are not random anymore. They are deterministic. I'm saying each number can be characterized as, each number can be written as some odd number times the power of 2. For instance, 6 is 3 times 2. 8 is 1 times 2 to the third. And I'm saying to each number like this in the series, I'm associated the size which is equal to 2 to the n. So to 13, I'm assigning size 1, because it's 13 times 2 to the 0. But to 8, I'm assigning 8, because it's 2 to the third. So I get, so essentially I get exactly this kind of a situation, of course. And then in order to prove, what is this? In any case, it's so the point is that I can do the same thing which I described to you. I'm now dividing each size by half. I'm ignoring the ones which were 1 and now they are less than 1. And then what happens? I get 1/2 1, 1/2 1. This is a new series after I divide. But then I ignore the halves. So I'm left with 1, 2, 1, 4, 1, 2, 1, and so on. Now, pay attention. What happens? The new series which I get is exactly the old series. So this is this self-similarity. And we finished our time, but essentially, and we are going to have a long vacation. You have time to study at home the things which are left unclear. I asked the assistant, actually, Nimrod, to give you quite a lot of explanations, additional explanations on that. But essentially, we finished by showing not only that this is a very predictive, powerful model, but in fact, it connects to all kinds of other beautiful things like fractals, and we'll go on after the vacation. I wish you a very happy Passover holiday. Bye.